So jumping into vector algebra, we've just done a whole investigation where we've come up with these properties here. And these are in our text, but I've just summarized them. We've got, if we add two vectors, the order isn't important, which is called the cumulative property, which is a handy one. We've also got, if we add two vectors and then add another one, it's the same as if we added the two other ones and the original one. So this is sort of saying that it doesn't matter which vectors like we add in which order, or we add two together and then add the third, we're going to get the same vector out. The additive identity means it's sort of like in numbers, if you have 1 plus 0, you get 1 back. This is what this is saying here. It's saying if we add a vector to the 0 vector, we keep our original vector, or if the 0 vector is added to our the 0 vector is added to a vector, we get the vector back. Now this one here is the inverse of the additive inverse, which means if we add a vector and another vector and we get 0, it means that they have opposite components. Pretty much with only two vectors, you're talking about parallel vectors, but in this space, it's just a way of saying that, like, if we want to get back to the original spot we were in, we have to add the negative of that vector. Or if we have a vector and we add the negative multiplied scalar of that, we get it back. This one here, the distributive property, looks a lot like the distributive law, because it is, in that if we multiply a scalar by, if we add two vectors together, then multiply by a scalar, it's the same as multiplying the scalar by the individual vectors, then adding them together. This last one here, if we have the length of the vector Ka, so a scalar multiplied by a vector, the length of that is going to be the same as the absolute value of our scalar by the length multiplied by the length of A. Two other useful rules here. This is sort of like if we're trying to find x and x is added with A, using our rules, we can then subtract A from both sides and we get those values. I will do these more in depth in the examples below. Now, this is super important. We cannot divide vectors by scalars. Instead, we multiply by reciprocal scalars. So we don't do A over 2, A divided by 2, because we can't divide vectors. We multiply a half to every component of the units. Cool, we've rolled through them. Now, I'm going to sort of talk through these. Let's just do this with our algebra first. So we're trying to solve for x in these problems here. So the first step here would be, well, same as any other algebra, we want to add r to both sides. So we would get 3x minus r plus r equals s plus r. Okay, this means we got 3x plus the 0 vector. All right. Now, a lot of the time we're going to miss this step. I'm just showing it for the moment. We got s plus r. And then our next step here is 3x equals s plus r. And then we're going to multiply everything by a third. So 1/3 times 3 equals 1/3 s plus r. All right, now, ideally, this might just seem a bit like bizarre. Like it might seem like we've gone. I don't know. You might find these steps a bit bizarre, but like if you think about this in terms of the three-dimensional vectors we're dealing with, this is actually super handy, because this means we can sub our actual vector. Oh, hang on, I should finish here. They cancel, and we're left with x equals 1/3 s plus r. So this is handy because of the fact that if we were to solve this in this space, we would actually have to let's actually do it for this one. Actually, no, I will quickly do the other one and then I'll leave it so that way you can decide whether you want to bother with it or not. So this particular one here, we're going to go we're going to minus c from both sides, minus 2x. And remember that property that the order doesn't matter. So this is going to be d minus c. Okay, now I'm going to skip the 0 step on this one because that's just going to be negative 2x on this side equals d minus c. let's multiply by the reciprocal. So this thing here, I'm just going to multiply by -1 on 2. That'll help. And then this here, we're just going to move it out a touch so we can put our scalar at the start. And so we've got -1 on 2 times by D and C. Let's go back to blue. So this becomes x equals -1/2 D minus C. Now, I'm slightly different to the text because I've got a negative and negative. You can multiply them in and you get positive C, negative D in there. Now, I just want to go back to this. So we actually see the benefit of this. If you consider the 3 different operations we're doing here, I'm going to just copy this original line here, and I want you to think about this versus this. So we've used a bit of algebra to get a solution here. Okay, and if I'm looking at this as a 3-dimensional vector, this means this thing is 3, and I'm going to use our general form, so x1, x2, x3. Now, you'll notice I'm not using the SACE notation, and this is minus r1, r2, r3 equals s1, s2, s3. And so you'd put these all together, and the next line would be we'd get 3x1 minus r1, 3x2 minus r2, 3x3 minus r3 equals s1, s2, s3. Okay, and we would then have to make these equivalent. So we would then, I'm just going to bring this over. We would then write that we'd have 3x1 minus r1 equals s1. And we would then solve this for x by going 3x1 equals s1 minus r1, x1 equals s1 minus r1, all on 3. And so we've got these steps, and that's just x1. We then have to do x2 and x3. So you can see this is quite a cumbersome way to solve, whereas in this one, we used a little bit of algebra, and I now look at this, and I could straight off say that, well, our individual elements here, x1, x2, x3, solving for this unknown we want, are going to be equal to, and I've got here, it's going to be s1 plus r1 over 3, s2 plus r2 over 3, s3 plus r3 over 3. And this, you can see, because of the algebra, we get to the same answer, but we're significantly quicker in this space. All right, thanks, guys.